In addition to photoelectric effect, thermal effect, and the Compton effect, there are some other processes which cannot be explained using the wave theory of electromagnetic radiation. So in this session, we discuss those other photon processes which can be explained only with the help of quantum theory of electromagnetic radiations. So in all these processes, the photons interacts with the atoms or electrons by delivering energy in discrete amounts or in discrete bundles. So the first one is the pair production and pair annihilation process. In the process of pair production, the photon loses all its energy, and also two particles are created in this process, an electron and a positron. A photon is being materialized into an electron and a positron. So we know that positron is a particle which is identical in mass to the electron, but it has got a positive charge. It is the anti-particle of the electron. ഈ പ്രോസസ്സിനകത്ത് ഇലക്ട്രോൺ ഒരു ആറ്റത്തിൽ നിന്ന് ഫോം ചെയ്യല്ല. The photon is materialized into an electron and positron. So this electron was not the part of the atom before. So before this process, there was no electron, and the photon materializes into an electron and positron. So according to the law of conservation of energy, the photon energy, which can be represented as h nu or hf. In this textbook, it is represented as hf. So you can also use h nu is equal to the sum of the relativistic energies of the positron and the electron. So E plus is the relativistic energy of the positron, and let E minus is the relativistic energy of the electron. And we know that the relativistic energy is equal to the rest energy plus kinetic energy. So for the positron, it is mp into c square plus kinetic energy of the positron. So the rest mass of the positron is same as that of the electron. So we can write mec square plus k plus, and E minus is the rest energy of the electron plus kinetic energy of the electron. So we can write this as mec square plus k plus mec square plus k minus. So we can have 2mec square plus k plus k minus according to the law of conservation of energy. So k plus and k minus are always positive. So the minimum energy needed for pair production is h nu is equal to 2mec square when k plus and k minus are zeros. That means the positron and the electron created in the pair production process are having zero kinetic energies. So we know that mec square is equal to 0.511 million electron volt, and therefore 2mec square is 1.02 million electron volt, and therefore the minimum energy for the pair production process is 1.02 million electron volt. So the electromagnetic radiations in the energy range are usually gamma rays. So the pair production occur only for energies greater than this. So it is a phenomena which is seen in the gamma ray region of the electromagnetic spectrum. So symbolically we can write as in pair production process, a photon materializes into an electron and positron. And we have already seen that this process will not occur unless there is a nearby atom to supply the necessary recoil momentum. That means the law of conservation of momentum is not satisfied without the help of an external nucleus. So an external nucleus is needed for this process to occur. So this process will not take place in empty space. So an external nucleus is also there in this process and also before this process. And the electron is not produced from the nucleus, but the photon itself materializes into the electron and positron. The reverse phenomena where the electron and the positron combine to form a photon is called the pair annihilation process, and this process can occur even in the empty space. No nucleus or atom is needed for this process to occur, as long as there is a creation of at least 2 photons in the process. So, in the pair annihilation process, the electron and positron disappear and they are replaced by 2 photons. And now, the law of conservation of energy requires that the energy before the process is equal to the energy after the process. And the relativistic energy of the positron is MEC square plus K plus, and the relativistic energy of the electron is MEC square plus K minus. So the sum of these two energies is equal to the sum of energies of the 2 photons produced. E1 is the energy of the first photon and E2 is the energy of the second photon. So usually the kinetic energies K plus and K minus are negligibly small, and therefore we can assume that the positron and the electron are generally at rest. So when they are at rest, this K plus is 0 and K minus is 0, then E1 plus E2 is equal to 2 me c square. And the momentum conservation requires that these 2 photons have equal and opposite momentum. So the photons are produced such that the momentum is being conserved. So one photon moves in this direction and the other photon moves in the opposite direction. So the momentum before the process is 0, and therefore they have equal and opposite momenta, and therefore they have equal energies. So those 2 me square energies equally divided between those 2 photons. So the 2 annihilation photons have equal energies. So the 2 MEC square is 1.02 million electron volt, and therefore each photons have an energy equal to half of this 0.511 million electron volt, which is the rest energy of a single electron, and they move in the exactly opposite direction. So this is the pair production process. And now we discuss the interactions of photons with atoms. We know that the emission of electromagnetic radiation from atoms take place in discrete amounts. That means the emission of is characterized by 1 or more photons. So suppose when an atom emits a photon of energy E, then the atom loses an equivalent amount of energy E. So consider an atom which is at rest, and the initial energy of the atom is E initial, and the atom emits a photon having energy E. So after the emission process, the atom is having an energy equal to E final. So and this E final is generally associated with the internal structure of the atom. and we have law of conservation of energy and law of conservation of momentum. And according to law of conservation of momentum, the final atom must have a momentum that is equal and opposite to the momentum of the emitted photon. Since the initial atom has got no momentum, since it is at rest, so that therefore the photon has got a momentum. So 0, the momentum before the process, equal to photon momentum plus the momentum of the final atom. So they are equal and opposite, so that the momentum before the process and after the process are zeros. So the atom must have a recoil momentum and therefore a recoil kinetic energy also. So the law of conservation of energy requires that EI is equal to EF plus K plus E, where EI is the initial energy of the atom, EF is the final energy, K is the recoil kinetic energy, E is the energy of the emitted photon. So the energy of the emitted photon E is equal to EI minus EF minus K. So the energy of the emitted photon is equal to the net energy lost by the atom minus a negligibly small contribution due to the recoil kinetic energy. So this is the net energy lost by the atom EI minus F. So minus a negligibly small contribution to recoil kinetic energy. Now consider the reverse process where the atom absorbs a photon of energy. So suppose the atom is initially at rest, it must have a small recoil kinetic energy in order to conserve the momentum. So the law of conservation of energy requires that EI plus E, that is the energy before the process, energy of the atom plus energy of the photon, is equal to EF plus K. So here the momentum is photon momentum only, and therefore there is a momentum after the process. So therefore there is a recoil kinetic energy associated with this. So EF minus EI is equal to E minus K here. So the energy available in the absorption process is the photon energy minus a small recoil energy. So this recoil energy is usually negligible. So if this recoil energies are negligible, we can write EF minus EI is equal to E. So whenever an atom absorbs a photon, then the energy difference between the initial and final atom is equal to the energy of the photon. So in the emission process also, when the kinetic energy is 0 or recoil kinetic energy is 0, the energy of the emitted photon is equal to the energy difference between the initial and final levels. So we will discuss the photon absorption and emission process in detail in the next module. The photon emission and absorption experiment are the most important techniques for getting information about the internal structure of the atom. So we will discuss all this in the next chapter, and we can see that in this photon absorption and emission, the law of conservation of energy and momentum are satisfied, and thus photon emission and absorption can be explained only with the help of the quantum theory of electromagnetic radiation. So we cannot explain these processes with the help of the wave theory of electromagnetic radiation. Okay, thank you.